You've seen it happen. You ask ChatGPT to write Python code, and it spits out a script that actually works. You ask it to explain quantum physics, and it explains it better than a textbook. It feels like magic. But the secret isn't magic. It's just math, relentlessly applied to one deceptively simple task: predict the next token. In this video, LLM Pre-Training, we are going to pull back the curtain. You will see the exact pipeline that turns the raw, chaotic text of the internet into the foundation for models like GPT. We'll cover the core concepts, things like self-supervised learning, subword tokenization, Softmax prediction, and the cross-entropy loss function that drives the whole process. We will follow this simple roadmap from start to finish. Check it out on screen. First, in Part 1, data preparation, we'll see how to take raw internet text and turn it into millions of structured input and output pairs. The best part? It's completely free. Then, in Part 2, we'll dive into the learning loop. This is where the model predicts a token, measures its own error, and then systematically self-corrects. And it does this billions and billions of times. By the end of this video, you will understand the exact technical pipeline, the one that creates the foundational intelligence of an LLM. So let's start with a big question. Why did it take so long to build models like GPT? Now, if you think the answer is just more computing power, you're only half right. The real problem, the true billion-dollar bottleneck, was data. For decades, AI models learned through a process called supervised learning. Take a look at the diagram here. The idea was pretty simple. You give the model an input, like an image of a cat, and the model learns to predict the correct output, the word cat. It does this by comparing its prediction to a correct human-provided label. But there's a huge catch. Where do those labels come from? A human has to create them. And that is fundamentally expensive. I mean, think about the real-world cost of these labels. Check out the examples on this slide. If you want to train an AI on medical imaging, you need expert radiologists to sit there and label MRI scans. We're talking hundreds of dollars per hour. Or for legal documents, you need lawyers to classify contracts, which costs even more. This creates a brutal ceiling on progress. Look at ImageNet. It's a famous dataset that really kickstarted the deep learning revolution. It has 14 million labeled images. Now, that sounds like a lot, but it took years of effort and millions of dollars to create. And here's the kicker. It's just a tiny fraction of the billions of unlabeled images just sitting on the internet. Supervised learning hits a brick wall. How do you scale to trillions of examples if every single one requires an expensive human expert? This is where the revolution happened. The genius of models like GPT wasn't just building a bigger neural network. It was abandoning the need for human labels entirely. This breakthrough is called self-supervised learning. They found a way to make the data label itself. And this created a paradigm shift in scale. Just look at this table. In the old days of traditional machine learning, we get data sets measured in megabytes. And yes, they needed human labeling. Then, deep learning came along with data sets like ImageNet, measured in gigabytes. But still, we needed humans. Now look at the GPT-2 era. We're talking about 40 gigabytes of text. But the most important part is that final column. That final column changes everything. Suddenly, you're not limited by human effort. You have an almost infinite source of training data. A single 2,000-word Wikipedia article is converted into nearly 2,000 individual training examples. This results in billions of learning opportunities, all for free. We solve the data bottleneck by turning the internet into an infinitely large, self-labeling textbook. So how do you get trillions of training examples without paying millions of dollars to human experts? You make the data label itself. The breakthrough idea is deceptively simple. The task is this: predict the next word. That's it. That's the entire secret. No human annotation is needed. The text itself provides both the input, which is the sequence of words so far, and the label, which is the very next word. Look at this diagram here. If the input is the cat sat, the label the model needs to predict is on. It's all right there in the text. This is the core of self-supervised learning. It's the closest thing to a free lunch in machine learning. We promised you an algorithm, and here it is. Check out this simple, powerful engine that creates unlimited training data. Now, don't worry about the code details. The idea is really straightforward. It just takes a document, walks through it one word at a time, and for every step, it creates a new training example. The input is everything it's seen so far, and the target is the very next word. Let's make this crystal clear. Take the simple sentence, the cat sat on the mat. Now, look at this table. This one sentence becomes a full curriculum for the model. Let's walk through it together, step by step. For the very first example, the input sequence the model sees is just the single word, the. And its job? To predict the next word, which is cat. That's our first high-quality example. Okay, example 2. Now the model sees the sequence, the cat. What does it have to predict? The next word in the sentence, which is sat. Simple, right? And the process just continues. The input, the cat, sat, is paired with the target, on. The input, the cat, sat, on, is paired with the, and finally, the cat, sat, on the, is paired with the target, mat. So, one sentence gives us 5 high-quality examples for free. Now scale that up to the size of the internet. I know what you might be thinking. This seems way too simple. How can just guessing the next word teach a model to reason, write code, or explain science? Because to get consistently good at this task across billions and billions of examples, the model is forced to build a deep internal understanding of the world. Let's look at this prediction task here. Imagine the model sees, in Paris, the capital of France, the primary language spoken is. Now, what must the model learn just to predict that one word, French? Well, first, it has to learn grammar. It needs to know that the verb is likely going to be followed by a noun. Second, it needs to handle long-distance context. It has to connect the end of the sentence all the way back to the word Paris, which appeared many words ago. Third, and this is the amazing part, it has to learn world facts. It needs to know that Paris is in France and that they speak French there. And finally, it has to learn to ignore distractors. It has to figure out that the word France is the crucial clue here, not the word primary. So, to minimize its error across trillions of examples like this, the model must learn concepts, facts, and the relationships between them. It's not just memorizing sentences. It's learning the underlying structure of reality. So let's get into a really fundamental concept. A neural network doesn't understand the word cat. It doesn't understand grammar or sentences. A neural network understands one thing and one thing only: numbers. The process of converting raw text into a list of numbers the model can actually process is called tokenization. And trust me, it's way trickier than it sounds. At first glance, this seems simple. Let's take the sentence you see here. The cat quickly jumped. So, what's our first idea? Approach number 1. Why not just split by spaces? This gives you what we call word-level tokens. You can see the list. The cat quickly jumped. Seems logical enough. Okay, what about approach number 2? We could go even smaller. This gives you character-level tokens. Check it out. T, H, E, C, A, T, and so on. Both of these ideas sound pretty reasonable, right? But in practice, they create immediate and severe problems. Let's put them head to head. Now look at this table. We're going to compare word-level and character-level tokenization. First, let's talk about vocabulary size. With word-level tokens, the vocabulary just explodes. Think about it. Are jump, jumps, and jumping all different words? To the model, they would be. You'd need a massive dictionary. But with characters, the problem is solved. The vocabulary is tiny, just A through Z, numbers, and some punctuation. Okay, but what about unknown words? This is a big one. With word-level tokens, the model just breaks if it sees a new word it's never been trained on. But with characters, again, problem solved. You can build any word in the universe from individual characters. So characters are looking pretty good, right? Well, here's the catch: sequence length. With words, the sequences are nice and short. But with characters, you get these very long sequences. This creates a huge problem.
So let's recap. Word-level tokenization fails because the vocabulary explodes. And even worse, it breaks on any word it hasn't seen before. This is a deal breaker. Characters solve those problems. They have a small vocabulary and can build any word, but they create a new crippling problem: massive inefficiency. Learning relationships across really long distances, like from the start of a paragraph to the end, becomes incredibly difficult and computationally expensive. On one hand, you've got word level. It's efficient, but it's brittle. It breaks easily. On the other hand, you have character level. It's robust, but it's massively inefficient. We need a solution that gives us the best of both worlds. We need a manageable vocabulary that can still represent any word without creating absurdly long sequences. And this leads us to the clever, elegant solution that modern language models actually use: the genius of subword tokenization. The core idea is brilliant. Don't treat words as the smallest unit. Instead, break them down into smaller, common pieces, just like building things with Lego bricks. The tokenizer learns common subword pieces from the training data itself. Let's see how this works in practice. Check out this table. For a simple word like cat, it's just one token, cat. But for an adverb like quickly, it gets broken into two common pieces, quick-ly. And a verb form like jumping becomes jump-ing. That double hashtag, by the way, is just a special marker. It tells us that this piece is attached to the previous one. This single elegant solution solves all of our earlier problems. First, it creates an efficient vocabulary. Before, this was really wasteful. You had separate entries for jump, jumps, jumping, and jumper. That's 4 different vocabulary slots. But now, it's so much smarter. You just need the main stem, jump, plus the little pieces like s, ing, and Second, and this is the big one, it means there are no unknown words. How does it handle a challenge like a new word, hyperthreading? Simple. It just builds it from its Lego bricks. Hyper, out, thread, ing. Itational. What about a typo, like awesome? It might break that down into awesome, M-M-E. The out-of-vocabulary problem is solved. Okay, so after splitting the text into these pieces, there's one final step. We look up each token in the vocabulary to get a unique integer ID. So as you can see in this little table, the becomes 5, cat becomes 8, quick becomes 73, and so on. Let's walk through the full process for the sentence, "The cat quickly jumped." Step 1 is the input text itself. Step 2, we do the subword splitting, which gives us the, cat, quick, ly, jump, ed. And step 3, the final output, is just that list of token IDs, 5, 8, 73, 152, 311, 94. This final list of numbers is what actually gets fed into the neural network.
But here's where it gets interesting. This brilliant engineering solution has a hidden cost, a, quote, dirty secret that explains some of the weirdest failures you see in LLMs. Have you ever asked a powerful model a simple question like, how many R's are in the word strawberry? And watched it fail? This is why. You, a human, see strawberry. It's one object, easy to scan and count, 3 R's. The model sees 3 abstract alien symbols. Let me show you what the model actually sees. Because of subword tokenization, the word strawberry
becomes 3 separate tokens. Let's say one symbol means STR, the next one means and the last one means berry. Now, imagine I asked you how many R's are in those 3 symbols. You'd have to mentally decode each symbol back to its letters, keep track of where the R's are across the symbol boundaries, and then count them. That's exactly what the model has to do. The letters are hidden inside the tokens. The model doesn't see individual characters. It sees these learned chunks. So tokenization gives us efficiency and power, but it also creates these strange blind spots. We've turned our raw text into a clean sequence of token IDs. This is the final input. We're now ready to feed these numbers into the model.
How does the model go from billions of internal calculations back to a single predicted token? This brings us to the elegant math of prediction. But first, we have to clear up the biggest point of confusion about how LLMs work. There are 2 completely distinct processes, and you have to understand the difference. First, you have training. During training, the goal is to output probabilities for every possible token. Then we calculate the error, the loss, and the model learns from its mistakes. The only goal is to get better. Then there's generation. This is when you're actually using the model. It still produces all those probabilities, but this time we use them to sample just one token to create new text. 2 different jobs, 1 mathematical foundation. Let's break down that foundation. After all the complex work inside the transformer, the model outputs a raw score for every single token in its vocabulary. This score is called a logit. Now, these are just raw, uncalibrated numbers. They aren't probabilities yet. They can be positive or negative, and they definitely don't sum to 1. Look at this example. After the input, the cat sat on the model might output these logit scores. You can see Matt has a high score of 3.2, Rug is 1.3, Floor is 0.5, and Moon is way down at negative 2.1. Clearly, Matt is the front runner, but these scores are messy. To turn them into clean probabilities we can actually use, we apply a crucial function called Softmax. Now, the Softmax formula looks intimidating, but I promise you, it's just a simple 3-step recipe. Check out the formula on the screen. All it's really doing is this. For each token, you calculate e to the power of its logit. Then you divide that result by the sum of all the exponentiated logits. This simple operation guarantees 2 things. First, every single probability will be between 0 and 1. And second, all the probabilities will add up to exactly 100%. Let's see it in action. We'll walk through our simplified example step by step. Look at this table. In the first column, we have our tokens. In the second, we have their logit scores. 3.2 for Matt, 1.3 for Rug, and negative 2.1 for Moon. Okay, step 2. We exponentiate those logit HTP. So e to the power of 3.2 is 24.53. E to the power of 1.3 is 3.67, and e to the power of negative 2.1 is a tiny 0.12. The sum of all those is 28.32. Now, for the final step, we divide each of those exponentiated scores by the total sum. For Matt, we take 24.53 and divide it by 28.32, which gives us our final probability, 86.6%. For Rug, it's 3.67 divided by the total, giving us 13.0%. And for Moon, it's just 0.4%. And what's the total? Exactly 100%. And just like that, the model's messy scores are transformed into a clean, understandable probability distribution. We have an 86.6% chance for Matt, 13% for Rug, and a tiny 0.4% for Moon. The model has officially made its prediction. We've reached the output probability stage in our diagram. So what do we do with this beautiful distribution? Well, if we're generating text, we'd sample from this to pick a word. But we're not. We're pre-training. Our goal is to learn. And to learn, we need to know how wrong we were. During training, we know the correct answer was Matt. Our model assigned an 86.6% probability to it. Was that good enough? How do we turn this into a single error number? That brings us to the heart of the learning process, the loss function that drives the entire system. All right, so where did we leave off? The model made its prediction. For the input, the cat sat on it gave us this clean probability distribution. The correct next token was Matt, and our model was pretty confident, giving it an 86.6% chance. But here's the billion-dollar question. How does the model learn from this? How do we turn that 86.6% into a signal that says, good job, but you can do better? We need a way to calculate a single error number, a score that tells the model exactly how wrong it was. This is the job of the loss function. And for language models, the function of choice is called cross-entropy loss. Now, the math behind cross-entropy can look terrifying, but the intuition is incredibly simple. It all comes down to one idea: surprise. Think about it. If you predict the correct answer with high confidence, you're not surprised. This means a low error, so what we call low loss. But what if you predict the correct answer with very low confidence? You'd be very surprised it was right. This means a high error, or high loss. The entire goal of training is to adjust the model's weights to minimize surprise over the whole dataset. So how do we calculate this surprise? Check out this formula. This is cross-entropy loss, simplified for our task. The loss is just the negative log of the probability of the correct token. That's it. That is the entire formula that drives learning.
We only care about the probability the model assigned to the single right answer. All the other 50,256 probabilities, they get ignored for this calculation. Let's walk through this with our two scenarios. First, a good prediction. As you can see on the slide, the model assigned 86.6% probability to Matt. So the loss is the negative log of 0.866, which is about 0.14. That's a really small number. It's a low surprise event. The model gets a tiny good job signal. Now let's look at scenario 2. A terrible prediction. Imagine the model was way off and only assigned a 1% probability to Matt. The loss would be the negative log of 0.01, which comes out to about 4.6. That's a much larger number. It's a high surprise event. Now the model gets a massive, you were way off signal. This single number, this measure of surprise, is the engine of learning. This loss value is the starting point for the famous backpropagation algorithm. The error flows backward through the entire network, and it nudges billions of weights, all with one goal: making the correct answer more likely next time. Do this a billion times, and the model learns the deep patterns of language, grammar, and even world knowledge. Okay, so that's how the model learns. It's a closed loop of predicting, measuring surprise, and correcting. But that's all for training. What happens when we actually want to use the model, when we're not trying to learn, but trying to create? When you call the OpenAI API or use ChatGPT, you're in generation mode. The model produces the exact same probability distribution, but instead of calculating loss, it has to pick a single word. Now, you might think, easy, just pick the word with the highest probability every time. But that would be a disaster. The text would be completely deterministic, incredibly boring, and it would get stuck in these weird, repetitive loops. To create interesting and creative output, the model samples from the probability distribution, and we get to control this sampling process. If you've ever used the API, you've definitely seen these parameters. Look at this code snippet. We've got our prompt, the weather today is, and then these two numbers, temperature and top P. So what do temperature and top P actually do? Let's break them down. First up is temperature, the creativity knob. Its mechanism is actually pretty simple. It modifies the raw logit scores before they go into the Softmax function. Check out the formula here. The adjusted logits are just the original logits divided by the temperature. So what does that do? Well, if you set a low temperature, like 0.2, the distribution gets much sharper. The model becomes very confident in its top pick. You'd use this for things like factual answers, where you want precision. But if you set a high temperature, like 1.5, the distribution flattens out. This gives the less likely, more creative words a better chance of being picked. You use this for more creative outputs. Next, we have top P, the quality filter. Top P, which is also called nucleus sampling, is our diversity filter. Its job is to let the model be creative, but stop it from saying something completely nonsensical. Instead of considering all 50,000 possible tokens, it works like this. First, it sorts all the tokens by their probability. Second, it adds them up one by one until it hits the threshold you set. And finally, it samples only from that little group, that nucleus of plausible tokens. So, if you set top P to 0.1, the model is only allowed to sample from the most likely tokens that make up the top 10% of the probability mass. This is very focused and safe. But if you set top P to 0.9, the model samples from a much wider nucleus of plausible tokens. This allows for way more diversity, without ever even considering the garbage tokens way out in the long tail. Let's see this in action. It'll make everything click. Look at this table. It shows how changing the temperature dramatically alters the final probabilities for our prompt, "The weather today is." At the base temperature of 1.0, sunny has a 40% chance, cloudy has 30%, and so on. Makes sense. Now, look what happens when we drop the temperature to 0.5. The distribution gets laser-focused. The probability for sunny jumps from 40% to nearly 63%. The model becomes almost certain that's the right word. Okay, now let's crank it up. At a temperature of 2.0, everything flattens out. The probabilities get much more even. And look at the word beautiful. Its chance is now jumped up to about 14%, giving it a real shot at being selected. It lets the model be a little more poetic. And that is the complete output pipeline. We go from raw logits to probabilities, which drive both the training loop and the generation process.
And that is the complete pipeline. You've now seen the entire journey from a raw text file on the internet to a sophisticated model capable of both learning and creating. You started this video seeing language models as magic. But now you know the truth. It's a cascade of brilliant, interconnected ideas, all powered by a simple, elegant process, learning from mistakes on an astronomical scale. You have now mastered the fundamentals of pre-training. Let's quickly recap the core engine you just built. Check out this slide. There were 3 core ideas. First, we solved the data problem with a self-supervised approach. By framing the task as simple next token prediction, we turned the entire internet into free training data. Second, we bridged the gap between human language and machine numbers using tokenization. We broke down text into these efficient subword pieces that the model can actually process. And third, we closed the learning loop. We saw how Softmax creates probabilities and how the loss function tells the model how wrong it was, allowing it to predict, get feedback, and learn over and over again. But our journey isn't over. Not even close. This pre-trained model is a raw engine of knowledge. It's an incredible predictor, but it's not a helpful assistant.
This leads to the 2 crucial questions of what comes next.
First question, opening the black box. Throughout this whole video, we've treated the core of the network as a black box. But how does it actually remember the word Paris from 10 tokens ago? How does it weigh the importance of different words to understand the real context? Well, that all happens inside the black box. And in the next video, we're finally going to open it. We'll explore the revolutionary transformer architecture and its core engine, self-attention. Now, for the second and maybe bigger problem, going from a predictor to an assistant. Here's the thing. A next token predictor is not a chatbot. If you give our pre-trained model the prompt, "What is the capital of France?" its training on all that internet text might just lead it to complete the sentence with another common question like, "And what is its population?" It's just completing a pattern it's seen before. It's not actually answering your question. Turning it into a helpful assistant requires a second, crucial stage called post-training. This is where we introduce powerful techniques like supervised fine-tuning, or SFT, and the very famous reinforcement learning from human feedback, RLHF. That's how we align the model with what we actually want it to do. You now have a solid foundation in how these incredible models are built. The magic has been replaced by understanding, and you're ready to explore the deeper layers of modern AI.